The topic electronic thermal management need basic level of understanding of fluids and heat transfer, and it is presumed that participants are from engineering background, maybe as a student of engineering or engineering graduate or an expert from industry. And most likely, I presume that the participants are from electronics or mechanical background. Though the subject does not have such constraint, but anyone having basic understanding of fluid or heat transfer can enjoy the session. So based on this perception, I'll try to cover general scenario of heat transfer and its side effects and effects on electronic components without having much focus on technical or mathematical details. And it also advocates the objective of the session. The objective of session is to give a general and basic understanding of electronic thermal management or the effect of thermal on electronics component. So in today's session, we are going to touch the following topics: electronic as a part of life, how it became omnipresent. Without electronics, we can't spend even a single second of our life. And why do electronic get hot? Then we will just set up a basic fundamental landscape for temperature. Then we will just touch up why thermal management is necessary. Then we will see Moore's law, temperature dependent failures, and role of CFD in electronic cooling. And then after at last the most important part, which is career path. So I'll start the presentation. So in today's era, electronic became a part of life. We can't even imagine a single second without support of electronics as it is omnipresent. So from the start of day till night, we are surrounded by electronics. I'll take example of my today's routine. When I woke up with the alarm clock of my mobile phone, and I turned off the AC. Then I used water geyser. Then I used microwave oven for my breakfast, and I put my leftover on refrigerators. Now I am giving this session on laptop with the help of internet connection, which is supported by modem. So you can see that electronics is everywhere. There is all and every part, every second, every moment of our life is supported by electronics. We today in today's era we could not able to thought of our spending our single second without electronics. So but if you remember, once electronic was a status symbol, electronic gadgets was a status symbol. I remember when we got first telephone in 1999. uh, it was a only way of communication for my whole society, and I was the messenger for my neighbors. My grandma used to drape it with a silk cloth because it was a status symbol at that time. It was a showcase piece for our family. But now everyone have their own mobile phone, smartphones, smart TVs, IoT devices are entering in our life. They are turning from status symbol to the necessity. So electronics is influencing our life in every possible way. You can say whether it is aero, auto, your kitchen equipments, your entertaining equipments, your basic necessities like alarm clock, or whatever you can see electronics everywhere. Though it is omnipresent, we can't we used to avoid this fact that electronics is everywhere. But if you imagine, if you just give your focus to the things, you will find electronics everywhere, surrounding your lifestyle, supporting your lifestyle in every possible way. So let's start. Why do electronics get hot? This is the major problem, and we need to address this problem. That's why we are here. So let's start. Why do electronics get hot? So you must have felt that while using your charging your mobile phone, uh, you some time feels that it get hot. Or you must have wondered why we have CPUs, why we have fan in CPUs and laptops. I want your focus on your 8th grade standard basic physics. We have learned about free electronics in conductors. When electrons move in a conductor with influence of potential difference, they collide with atom and the lattice structure of the material. During this process, there is a transfer of energy in form of momentum and heat. In modern electronic devices, there's lot of electronic components stack up in a small space. All have their own unique specification and require different amount of current. For example, if you have a smartwatch or a smartphone, it is having a chipsets which have lot of transistors, and every transistors or every resistors have their own specification and own need of current. So to resist the flow of current, we use resistance or we use resistors which act as a resistance to the flow. And when there is a resistance to the flow of current, the energy got transferred into heat. So you can say that higher the resistance, higher the heat energy dissipate from the conductor. So now we have developed a basic understanding that why do electronics get heat up. So that's why we use nichrome wires in our electric heaters. You can see that here in picture 2 we have a electric heater. It's a generic electric heater, and we use nichrome wire set up in the rods to get the heat. So with this understanding, I left a question for you to give you a thought that why the coil of electric room heater wounded in a circular pattern. So you just give a thought on that, and I presume that if you recall your basic 8th grade physics, you can get the answer of this. Before jumping to the main focus section of the webinar, let's establish a basic understanding about temperature. Please do not get confused with heat and temperature, as heat is energy and temperature is a measure of that energy. So have you ever wondered about the temperature of the iron which is glowing at like gold, or the temperature of ice cream you have eaten last time? I don't think so. So let's see. If you, I want your focus here on this landscape, and from here I try to establish a basic platform or basic understanding of temperature. At 530 degrees Celsius, iron starts glowing as dull red. 230 is typically temperature of pizza microwave oven, and at 200 degrees Celsius, shoulder of electronics get melt. 105 degrees Celsius is a maximum temperature which a PCB board can hold. 100 degrees Celsius is, we all know that it's a temperature of boiling water. 85 degrees Celsius is maximum ambient temperature which Intel use as a standard. 80 degrees Celsius is a typical temperature of the sauna. 65 degrees Celsius is maximum ambient temperature which used by automotive industry. Here Hero, Yamaha, everybody use 60-65 as a maximum ambient temperature. 58 degrees Celsius is the highest temperature recorded, but this year I think this record will be broken because of global warming. We are getting lot heated temperature over the region somewhere in Canada and African region. 50 degree Celsius is the ambient temperature for telephone central offices. 32 degree Celsius is uncomfortable temperature. When you are sitting in a room, you will feel little uncomfortable at 32 degrees Celsius. And minus 16 degrees Celsius is the temperature. It's the best temperature at which ice cream has to be served. So, and minus 273 degrees Celsius is the absolute temperature. So I just want to develop a basic understanding of temperature with this. Now let's jump to the main topic. Why thermal management is required, or what is the necessity of thermal management? As you all know that in early eras, computers are gigantic in shapes. They require space more than a room. So you will be amazed to know that the size of your mobile phone, the memory, 256 GB memory is equivalent to 54 Olympic size swimming pool completely filled in 1958 by hard drives. In 1956, IBM launched first computer which is named as IBM 305 ROMIC. The weight of that computer's hard drive is over a ton. So with the advancement of the time, electronics are reducing the shape. It's becoming more compact and more cheaper as well. The 8 TB Seagate model in Amazon, you can go to Amazon and just check the 8 TB hard drive. You can get it in 10,000 to 14,000, which is 300 million times cheaper than the first hard drive, which was made by IBM. So, with time and advancement of technology, electronics is getting compact and cheaper. It is becoming necessity of life. So, with this advancement, there is a need of thermal management, and it will be more clear when we will see Moore's law. Gordon Moore is a founder of Intel, and he gave us a law which says that the transistor in a dense IC doubles every year. Like in 1970, there is close to 1,000 ICs, but in 2015, the number got exponentially got doubled, tripled every year. So it is possible because only because of evolution of transistors. If we see the origin and evaluation of transistors after World War II, it is the greatest invention that changed the world completely. It made our space travel possible. Mobile phones are into existence only because of transistors. I personally feel that after invention of electricity, the greatest invention is the invention of transistors. Transistors are very simple. They act as a switch for electrical signal. You would be amazed to know that recent Apple phone have an IC which is few centimeter square of area. It is very small. You can hold in your using two fingers, and it have 8.5 billion transistors. So the objective of last few slide is to give you the fair enough idea about how electronics is reducing its shape, reducing the cost, and how it is omnipresent in our current life. So when is reducing, there is 8.5 million of transistor in single IC. every transistor is dissipating some power and getting heat up. So there is need for thermal engineer to manage the thermal part, the heat part. So now we'll discuss, okay, some has to manage the thermal part, but why some has to manage the thermal part in electronics? What kind of failures we can get in electronics? So we will see that there are some temperature dependent failures, and temperature dependent failures majorly you can classify into three category. And first one is temperature dependent mechanical failure. So before that, I'll just explain. This is a basic bond wire BGA. So in this bond wire BGA, I'll just need your focus. The Where you will see the pointer, it is a mold resin. It is called as encapsulant. Beneath that encapsulant, we will have dye which is generally made up of silicon. And again we have this sitting part. So there are, this is a, you can say that three blocks are stacked up in a geometry, and these are the wires which is bonded using some bonding adhesive. And we have shoulder bolts. You can check this kind of BGAs, you will find it on PCB of your laptop or TV or mobile. Mechanical students, please don't get confused. You can consider this as a stack up of three blocks with a heat source. Die is generally the heat source. So uh, let's take an example that die is a heat source emitting 2 ampere as a current and 2 volt as a potential difference. So the total power emitted by this die is around 4 watts. So now we know that 4 watts is emitted by this BGA, and it will give some temperature to the nearby components as well. So we need some expert to check whether this temperature will cause any damage, or what kind of damage was caused by this temperature. So first criteria is temperature dependent mechanical failures. So you can refer mechanical failure as deformation, yield, crack, or fracture in the material, or as joint or shoulder bolts. It happens because of high thermal stress or repetitive load like thermal fatigue load. Wherever fatigue comes, you have to consider it as a cyclic or a periodic load. Small but repetitive thermal loads can also be catastrophic for the design. You can correlate this load, like for example, you have a aluminum rod and you bend it to and fro. Maybe the load was not so high to crack the aluminum rod, but the to and fro motion made it possible. So repetitive loads are catastrophic for the components. So whenever you have the repetitive load, we will use a word fatigue. And in mechanical dependent failures, we just generally classify it into a three parts: wire fatigue, wire bond fatigue, and die fractures. So wire fatigue, it as term says that it has fatigue, so indicating a repetitive thermal load. So in wire fatigue, the load is not too much to crack the wire, but it will affect the integrity of the joints when the temperature increases and decreases. One more point is that every material have its own expansion coefficient. So whenever the temperature increases or decreases, there is a contraction in material and there is an expansion in material. So this frequent contraction and expansion of material is considered as thermal cyclic loading. So in wire, when we will get this contraction and expansion, it affects its integrity and it made the connection loose or it fails the connection. In similar way, we have wire bond fatigue. In wire bond fatigue, as name indicates that we have a thermal cyclic loading. It fails the wire and the bond. Here you can see that we have the bond of wire with die and the sitting part. So if that bond fails, there is a loose connection and there is a open circuit. So it fails the component. In similar way, we have a die fracture. You can see that there is a sharp corners over here in the die. So in this die, the most evident and important part is the die of this component. Since die is made up of silicon or germanium or arsenide, and substrate is typically made up of aluminium. So both the materials have their own coefficient of expansion. Because of the cyclic loading, the shear stress develop at the corner of the die. And because of this shear stress, crack develops. Crack start developing over the die and the component fails.